calculating the x component, y has to be 0, and for y to be 0 we have to keep both y's as equal, so that whenever we calculate, yeah, so these are the 2 points, these are the two things that account for the offset. So we will have an offset x and an offset y as well. Cos of lat1, cos of lat1 into cos of lat2. Let's see if that works. Yeah, now it works fine. Yeah, perfect. So hi everyone, in this video we will be building maps from UI to the backend as well. We will try to not use any libraries. We will not use any libraries. We want to build it from scratch. Otherwise, it would be a very easy thing if you use libraries. Just take something from Google Maps, a static library from Google Maps, or any other API. Then you can add routing and you can get everything, every service is available. So we are aiming to develop that service itself. So we'll be building the interface from scratch as well as the backend from scratch. The backend will not be that important. We just have two things in mind that we want to do, and that is creating a map interface and also routing. So these are the two things that we have to do. So the map interface will look like Google Maps, obviously. We will not be taking the entire globe because it will be a lot of data. We will just take some area. So this is the area of Connaught Place from Delhi, and we'll build a map for this place and then try routing from one point to the other and see if it works. So this is what we are going to do. So basically in this map, if you look at this map, how might this be built? So this is built out of pixels. So there might be something like for every coordinate, there is some pixel that is present on this map, and to that pixel is attached different attributes like latitude, longitude, and other sort of things. So this is how basically this might have been built. Obviously, I don't know how this is built internally. So the approach that I'll be following here, I don't know if it's right or wrong or if it works or not, but let's just try this approach. So in the approach that we'll be using here, we have different nodes where multiple roads connect. So we will be taking advantage of all these nodes. So let's say if this is a node, and for this node we have the coordinates available, and this node is connected to a node behind, a node in the forward, and a node and some node in the other direction. So that we will be taking into account in the node. In all of these are the neighboring nodes for this node. So we will create a graph out of it. Once the graph is created, then routing is not a big thing. We will simply have to apply the Dijkstra's algorithm, which will give us the shortest path simply, and to calculate distance between 2 points. So basically, we will be having the latitude and longitude only. So on the basis of these coordinates, we will be having to calculate distance of this distance between 2 points. That can be done using different formulas. So so there's this Haversine formula. So what Haversine formula does is a accurate way of computing distance at between 2 points on the surface of a sphere. So it is important because the Earth we cannot simply calculate using the linear formula, which for of calculating length between 2 points. We will have to take into account that the Earth is a sphere, because of which we'll be applying the Haversine formula. Obviously, it is not completely accurate, but this is the most accurate that we can go up to. How does Google Maps calculate distance between 2 points? So this is known as the Haversine formula. So Haversine formula is used by Google Maps as well. We'll be using the same thing. And once so that would be the backend part, which will come up later. First of all, we will be figuring out how we can build these roads. So the important thing was that we are going to build this using graphs. In graphs, we will be having these points, these nodes. These nodes will be having some neighboring nodes, and we will construct the entire graph accordingly. Once the graph is constructed, we will try joining these points. Now the other another important thing is how will these nodes be there? So these nodes will be in the form of an object. This object will consist of these fields, and one is the latitude, then you have the longitude, which represents the coordinates on the earth. Along with that, we will be having these two things, drivable and walkable. Let's not keep walkable, and I guess drivable is also not needed because we are building for roads only. So yeah, let's just drop drivable as well. And also we will be having these neighbors. So it's basically a node of a graph simply. In the front end, we will be using the Canvas API. Now the task here is that, let's say this is our screen. Whenever we use a Canvas API, the point here in the top left corner is considered to be the origin, and the positive x-axis is towards the right, and the positive axis is downwards. So this is a bit different from the Cartesian plane. Oh yes, so this is how our canvas is going to look like. In the right hand direction, we'll be having x coordinates, and in the and downwards, we'll be having y coordinates. So what we basically have to solve is that, okay, so for some latitude, longitude, we will be assigning the origin. And so the origin is going to be at the top left corner. And yeah, so this is the origin. And we will have to do everything with respect to the origin. Okay, so basically, the object that we have. So this object is basically good enough for the data used for calculating distances and stuff. But this is the real data. But we have to virtualize this data and we have to visualize this on the screen. So how we will also need the x and y coordinates. That will be no, but even if we put the x and y coordinates, it is going to change because we also need to implement a feature of this sort. When you click and drag, you need this to uh, pan along the screen, and when you pan it, the x and y coordinates of any latitude, longitude would keep changing. So this is something that we don't want. Obviously, x and y is something that we don't want because we have to take care of the fact that we are going to pan and zoom, and whenever you zoom, the coordinates change. Whenever you pan, the coordinates with respect to the screen changes. So that is why we will not take into account the x and y. The object is fine, object looks fine. Okay, so let's see now how are we going to set this up. So we have these things that the 0, comma 0 origin is going to be the top left corner, and this is the default property of canvas. And towards the right we will have positive x, and downwards we will have positive y. Now the next thing is that we will have to decide how much of the map we are going to deal with. So what we will be doing is we will have to calculate the x and y coordinate on the basis of the latitude and longitude of the reference point, which would be the origin, and the latitude and longitude of any point that we are dealing with. So first of all, we'll find the reference point. The reference point would be the origin, and that would be at the top left. Okay, so let's take somewhere here as the reference. And these are the coordinates of the reference. So I'll just copy this, and yeah, so these are the reference coordinates. Let's say we have this point. We have a reference point that we got. Now from this reference point, we will be normalizing all the other points onto this screen, that is onto this canvas. That for that we need this reference point. How are we going to do that now? So first of all, let's say if we take any other point on this map, if I simply take this point, okay, so the reference point was somewhere here, and okay, so let's say if I take this point has these coordinates, So now, how will I place this point? Where will I place this point on the screen? For that, I need to know the x and y coordinates of this point with respect to the origin and with respect to this point. So how will we do that? So first of all, approach that comes up in our mind, that would be first you calculate the distance along x, then you can calculate the distance along y, and whatever you get would be the point on this canvas. But the distance that we get from these 2 points would have to be accurate, and for the accuracy, Earth is a sphere. We cannot use formulas of a plane over here. So what we will be doing here is the will be using the Haversine formula that I had mentioned earlier. So if we look at this formula, okay, so this is basically the formula, the Haversine formula. We'll be using this formula. We also have a code over here that we will be taking reference from. So if you want to calculate the distance, so for that, first of all, we have to convert all the latitudes and longitude into radians. Once we convert it into radians, we calculate the deltas of latitude and longitude. It might be, I mean, we can do this anyways. First convert it into radians and then calculate the delta, or first calculate the delta and then convert it into radians. Once it is converted into radians, we apply the formula. So what is the formula? I'll just write the formula down. So this is basically the formula that we have to go on with. Here, what is more important is firstly we'll have the latitude plus the longitude. For longitude, we have this different terms which are coming up here. So why is it that, why is it there? That also I'll try to tell you about it. So I'll just write this formula over here, and yes, so the distance, let's say, Haverside. Okay, so this is the Haversine formula, and this is something that we are going to apply. Now we have to place this point onto this canvas. How will we do that? First, the first and foremost thing is that we'll have to calculate the x component and y component of this point with respect to the origin. So how will we do that? So for the x component, what we have is we will have to calculate the Haversine distance uh, between the points. One would be the origin. So for origin, I'll take this point, and one would be the the point that we are dealing with. But along with that, the important thing is that we are going to calculate just the x component. So for x component, if we are calculating the x component, y should be 0. So y has to be same. Okay, so the point that we have added here is the reference point, and this is the final point. So the only difference here is that because we are calculating the x component, y has to be 0, and for y to be 0, we have to keep both y's as equal, so that whenever we calculate the Haversine distance, the difference between these two would be 0, and the only thing that we will be considering would be the y component, would be the x component. Along with x component, we also have to uh, have another one where we will be calculating the y component. So this is the y component. For y component, the reference would be same, and the point to which for which we have to calculate would also be the same. The only difference would be that the x coordinates value would be same for both the points, because now in this case we are calculating the y component, so we are not doing anything with x. Okay, so now basically we have the x component and y component. Once we get the x component and y component, we can simply just uh, just plot it out on the screen. But the problem is that if we are calculating the Haversine distance in this formula, the radius of Earth would be huge. And the distance that we would get is the actual distance, be it in kilometers or in meters or anything. It depends on what unit we use in this radius of Earth. So once we get the hours and distance, that would be a very huge value, which obviously we won't be able to plot it on the screen. So to plot it on the canvas, what we can do here is that we can just normalize this or both the values such that these can be plotted on the canvas. So for normalizing these values, what we can do is we can just simply get the okay, so this is the reference point. Along with that, we can also calculate the maximum x and y distance that the canvas is going to cover. If we have the maximum x and y distance, we can simply apply a formula so that we can normalize it to this canvas. So I'll just write this down here. So let's say we have to calculate the normalized x. So to calculate normalized x, we have, so this is not a component, it is the x distance, and this is the y distance. Okay, we will calculate the maximum distance from the origin that this map will be covering. Okay, so maximum distance that this map will be covering will be set by us. So if we have a max distance that, so max distance is the maximum distance along the axis that the map will be covering. Okay, so that max distance can be anything. Fine. Once we have this max distance, the next thing that we have to do is simply get the ratio of distance. Okay, so we have x distance, normalized x. For normalized x, we will take the x distance upon max distance. This would give us a ratio. The value of this would be between 0 to 1. So once we get this, what we can do is the value that we have obtained in 0 to 1, we can just multiply it with the canvas width, so that we can get this x component onto this canvas within the canvas range. So what we have basically done is we have calculated the x distance with respect to max distance, the ratio of x distance with respect to max distance. This will give us a value between 0 to 1. Once we get that value, just multiply it with the canvas width. This will give us a normalized x that lies within the range of this canvas, and now that can be plotted onto our canvas for further usage. So yeah, so this is for normalized x. Similarly, for normalized y, we can calculate the same thing, distance y distance upon max distance into canvas width. So in this way, we will be calculating such distances for all the points that we have to map out on this interface. So I'll just sum it up with how are we going to go about this. First of all, we have an origin. We are not using the entire map. So we will be dealing only with a certain area. So for that, we are also keeping an origin as latitude, longitude, origin. So we are also keeping a reference point, and that is the origin, and that reference point is this point. Now from the origin, we have to calculate all the other distances such that all the other points such that we can fit them onto this canvas. For that, what we have done is, let's say we have a point of this sort. For this point, first of all, we'll calculate the x and y distances using the Haversine distance formula. Why are we using Haversine distance formula? Because Earth is a sphere, and for sphere, the distances between 2 points depends upon a lot of things that the Haversine distance takes care of. So this is the Haversine distance formula, which is 2 into radius of Earth into sine inverse of square root of sine square delta of latitude by 2 plus this term. So this is for the longitude normalization. This is for the latitude. Why do we have these terms in longitude? Because whenever you look at globe, if you look at a globe, the longitude at the poles are shrinking down and coming together, and they have lesser distance as compared to other points on the surface of the earth. So to adjust that, we have these elements over here. And so this will give us the Haversine distance of x and y. So along x and y of this point, so we are calculating the x component and y component basically. Now we also have a max distance that we are going to plot on this canvas. So the max distance would be the maximum distance that the map is going to cover, because we are not covering the entire map or the entire globe. So we have this max distance as well. Once we get this max distance, now we can calculate the normalized x and y that we are going to actually plot on this canvas. So for normalized x, we have this formula x distance upon max distance, which will give us a ratio between 0 to 1. Once we obtain this ratio between 0 to 1, we can plot it onto canvas width by multiplying it with canvas width. You can just get the value on the x-axis such that it lies within the canvas width and also satisfies the Haversine distance and all the constants that it has to satisfy. So it's just that all other points will also be with reference to all of this calculation that is being done, and that will create a map for us on this canvas and we can further use it. So just a quick change here, it would be canvas height for the normalized y. And yeah, so this is how the entire thing is going to go about it.